kindly invited to release them. I'm sure because he was the lead on what is expected.
It is my great honor to release Vikash's. This is volume 2 of the collected works. It is my pleasure to release them. If you could do so now.
Chair of the cover in the absence. On your behalf. On your behalf. And I know what cover tearing means. And here we are, Raja.
Wonderful. I hope they've done a very nice job. I'm sure they will have done.
So that's as hefty as volume 1. Thank you.
Now we have Professor Sir Roger Penrose's talk, and I have great pleasure requesting, although very early in the morning in Oxford, to deliver his talk. It's very kind of you, Roger. We're all waiting here to listen to you. Sir Roger Penrose.
Thank you very much. I hope you can hear me.
Everyone who has joined online, could you please stop your video sharing because just for saving the network bandwidth. So,
Okay, good. Let me know when I can start. Okay, I'm afraid you should have a better picture of the opening slide, but perhaps that doesn't matter. This is cosmology, black hole singularities, and cyclic cosmology, or cyclic cosmology. So, I hope you could see this. This is not I sent a version of the entire slide, which I guess you don't have. Let's not worry about that. Can we move on to the first slide? This is a picture taken from my paper, which seems to have eventually got me a Nobel Prize, which is a space-time diagram, which describes. I published this paper in 1965. I gave a talk on King's College in 1964 about it. This was at the time when the quasar observations were beginning to be received, and people were very puzzled by the fact that they seemed to be very energetic objects, which nevertheless would vary. I mean, so energetic they are much more than maybe an entire galactic cluster, and they seem to vary in periods of just maybe a few days or something like this, which meant they had to be very small and very energetic. So people began to speculate that perhaps this was something like I should describe the Oppenheimer-Snyder collapse of a dust cloud, which was published in, I believe, just before the war, in 1939. And they considered a dust cloud collapsing. The dust cloud was exactly straight and symmetrical. Dust means there is no pressure. And in their model, the material collapsed inwards and inwards until it reached a place where the density becomes infinite and the space-time curvature becomes infinite. People were somewhat skeptical that this could be the result of a general collapse because, first of all, there was no pressure, but more importantly, it was exactly strictly symmetrical. Now, I published this paper because I considered a much more general situation. In this picture, you can see time is going up the picture. The little ring you can see at the bottom of the picture is what I call the trapped surface. You have to imagine, first of all, this is rotated about the central axis, and secondly, it's rotated through 2 dimensions, so you can't get a proper picture of what's going on. What looks like a ring, that little ring at the bottom, is what I call the trapped surface. There's an extra dimension, so it's really 2-dimensional. And the point about it is that in the Oppenheimer-Snyder collapse, you can find a ring like this, where if you kind of flatten the light on that ring, then not only with the inward flash, that's the sort of inward, you see the shaded region there, that is the boundary between the boundary of the future of that ring. So the future of that ring is the shaded region. The inner boundary would be going inwards, and what's funny about it is the outward boundary is also going inwards. This is a special feature of the spherical symmetrical Oppenheimer-Snyder collapse. Nevertheless, it's a stable feature, because you can perturb it. You can imagine you will put irregularities in, and if these irregularities are not too huge, they will leave this feature of the trapped surface unchanged. That is to say, the boundary of its future is locally goes inwards. And I studied such things, boundaries of future, in general case, and you could see that they had certain properties which were quite general and didn't necessarily depend on the spherical symmetry. Let's move on to the next slide. I want to describe the space-time picture. You see, in space-time, you have three spatial dimensions, so x, y, and z are the spatial dimensions. One time dimension, which is the t, and you want to adjust your coordinate of the passage of a photon would look like something reasonable. So if your spatial coordinates were in if your time coordinate was say in seconds, then your spatial coordinates would be say, roughly speaking, in light seconds. So that means that a photon, the trajectory of a photon would be something not horizontal or vertical, it would be at a reasonable angle. Okay, can I move to the next slide? If I consider the long photons through that particular point, they describe what's called the null cone. Of course, you have to imagine there's an extra dimension, but never mind, the pictures will do. The null cone describes all the multiple photon trajectories from that point. Can we move to the next slide, please? This is just the null cone, because we don't really want the axes, we're not interested in the coordinates, we're interested in the null cone itself. Can we move to the next slide, please? You see, in general, you'll have a space-time. I've only indicated as a surface, but you want to imagine as a 4-dimensional surface. At every point, you will have a null cone. I've indicated both the future and the past cones. I'm going to be concerned mostly with the future cones, but sometimes I draw them both. And you can make be scattered in different places in space-time in a general way. Can I move to the next slide, please? This is now going back to my picture, and I want to consider the boundary of the trapped surface. But now I'm perturbing this surface, so it's not exactly symmetrical case, it's irregular. Nevertheless, you can prove that the boundary of this surface is generated by null geodesics, by a straight line, you say, there, which would be tangent to the cone. And you can study these things and see their properties. Can we move to the next slide, please? You see, in general, you have a complicated situation where the light rays will start to cross over, and you might say, how can you consider such a complicated thing? Well, the great thing is that the boundary of the future did not include the cusps and all that complication. You see, you can follow the rays up until they are crossing each other, and after they cross each other, they enter the interior, and so the boundary stops there. You can consider this boundary, it really is topologically a nice surface, even though it's irregular, it's not smooth, because at each point, you can track backwards along the light rays. And that was the feature that I used to prove the theorem that showed that you would necessarily, in general, if the energy was not negative, you would necessarily get some contradiction which would be singularity. Can we move to the next picture, please? This is showing you what happens in general. I want to describe the two features of curvature of space-time. The curvature of space-time has two features. It's actually described in the next picture, but I want to go back to this picture if we can come to it. Can I go to the next picture? You see that right at the top of the picture, you see that there we're looking backwards. The light rays get focused in a different way. The Ricci curvature is what matter has, and this is like a positive lens. The light rays get focused inwards. It's the effect of a positive lens, a lens which magnifies. The free field is the Weyl curvature, which introduces distortion. I wonder if you could go back to the previous picture, it would be useful. Thank you. You see, if you can imagine that you look through the sun, and of course they're in the way, but if you can imagine the light rays going through the sun, the focusing would be positive. So it would be like a magnifying lens. So we push the background stars outwards. So you can see the deflection pushes it outwards. That's the focusing of the sun rays would cause the field outside the sun outwards. Now you're looking at another Weyl curvature, which not only is being pushed outwards, you get a distortion on the spherical patterns. You see a circular pattern of stars will become elliptical. This is this distortion due to Weyl curvature. So you have to imagine there are these two kinds of distortion. Can we move back to the next picture, please? That was just what I was talking about. And the thing is that there's always I want to go back to the previous one. Yes, but the light rays get focused inwards, and if you have Weyl curvature, even though it's just distortion, if you have lots and lots of Weyl curvature, it's still focusing inwards. So the focusing is always inwards. And this means that you will get, if you start by having an inwards focusing, when you have a trapped surface, then it will finally get to a point where you leave the surface. Anyway, the argument was, can we move to the next picture, please? Well, this is actually, it's not really what I wanted. Never mind. I showed you, anyway, the argument that I showed, you have positive energy, which means that the focusing is always inwards. You get a compact surface from the trap surface. And this leads you to a contradiction with the initially non-compact situation. You have this situation that shows singularities come about as long as you don't have negative energies in generic situations. I gave a talk about this at King's College and then a repeat talk at Cambridge. And Stephen Hawking was present at that repeat talk. And we then had a discussion with, I think it was George Ellis and Stephen Hawking and Hans Brandon Carter. And we talked about the technique I was using. Stephen then generalized my arguments by introducing new concepts as well to apply to the Big Bang. So it shows that if you have a singularity, the generic singularity, this picture I'm showing you here is not exactly the one we had then, because the normal picture of the Big Bang did not incorporate the expansion that we now see in the remote future, is the result of what people call dark energy. I prefer to call it Einstein's cosmological constant, which produces this exponential expansion. But we weren't familiar with that at the time, but nevertheless the general arguments that Stephen Hawking produced, and we collaborated later in a very general theorem, these were published in the Royal Society, and what we showed was that you couldn't get rid of this initial singularity just by introducing perturbations, unless you had negative energy or something like that. Can we move to the next picture, please? Now the thing was that this would also apply to the collapse. If you imagine the collapsing universe, then you would get these generic singularities. Now, I'm puzzled very much about this because in a generic collapse, we have something very complicated, which will not look like the general singularity. We have like holes. Can I have the next picture, please? It will not look like that because it will look something very complicated, like the picture here. The general collapse will involve many, many local collapses, black holes. These black holes will come congealing and produce an incredible mess. This mess does not look anything like the time reverse of the black hole that we see, the Big Bang that we see. Can we have the next slide, please? The next slide will look like a general Big Bang. General Big Bang will be something like this, not like what we actually see. People used to argue, I think, that in the early universe that you would have this phenomenon called inflation. When we talk about inflation, it doesn't really help. But it was, I think people thought it helped you. Can we move to the next slide, please? You see, if you put a magnifying glass to what the Big Bang looked like, then the current view was that you would have something like inflation. Can we have the next slide, please? So you would have something like an exponential expansion, and this was supposed to smooth out the universe. Well, it doesn't smooth the universe, because in the general situation, you will have this complicated case. Even with the plate you put the top field in, it does not affect the general case, which would be this very complicated analytical situation. Can I have the next slide, please? I want to talk about, you see, this is all connected with the second law of thermodynamics. The second law of thermodynamics tells us when you go back in time, the entropy of the universe gets lower and lower. Now this is a picture that was produced in the very first satellite, the Kobe satellite, which showed this remarkable picture of the microwave background. Here we have the temperature is the horizontal axis, and the vertical axis is the intensity. And we see this microwave background where the error bars, obviously the bars here, but they are magnified by a factor of 500. So that if you had them actually as the error bars really are, they would be easily within the incline of this curve. It's an extremely accurate picture of the Planck curve. Now what does the Planck curve tell you? The Planck curve tells you that you are looking at thermal equilibrium. That is to say, the matter and radiation is at a maximum entropy. Now this to me is a huge puzzle, because it's telling you go back and back and back in time, and what is the earliest thing you see? The earliest thing you seem to see is thermal equilibrium. The entropy should be coming down and down and down and down until you reach this maximum. Why do you reach a maximum? It should be a very small entropy. It's not a contribution because of, can we see the next slide, please? This is showing you, comparing in the top three pictures, we have a gas in the bottom. Now, if you imagine the gas in the bottom, which is initially constrained to one corner of the box, you will wait the gas spreads out and spreads out until it's uniformly distributed through the bottom. So what you see is an increase in entropy and an increase in uniformity. So this is very much like what we see, maximum entropy state. However, it's not a picture because we also about entropy. I want you guys to imagine a box which is a galactic scale box with a lot of stars in it. Now, as the stars, as the entropy increases, the stars have collapsed, the stars come together, and the entropy increases, but you have less and less uniformity. And you get black holes, where the entropy goes shooting up to an enormous number. So what we actually see is a combination of the matter being black to entropy uniform, and the gravitation being low entropy. You see uniform distribution, which is telling you that what you're seeing is in the gravitational context a very low energy. So to me, it's a huge puzzle, because you are seeing the gravitational degrees of freedom, and to me that means the Weyl curvature, the gravitational Weyl curvature, is for some reason set to 0, or very, very low. And you're not seeing that in this maximum energy state, which is black hole. So to me, this was an extremely big puzzle, which people not to worry about so much. Can we move to the next slide, please? Now you see, this is describing the Schrödinger pointed out this thing which I think many people find puzzling. What do we get from the sun? You see, life on Earth depends on the sun. And people say, well, we get energy from the sun. We don't get energy from the sun, because in the daytime we get the energy. In the nighttime, it all goes back again. And we actually get slightly more because of global warming, but the major effect is that all the energy goes back to the sky. But the point is, we get the energy from the hot sun, which is much hotter than the sky. This means that the energy from the sun comes in a relatively few high energy individual photons and goes away in low energy, many, many, many degrees of freedom, low energy photons. So what we get from the sun is the hot spot in the dark sky. It's the imbalance between the sun being very hot, and the sky being dark. So the wonderful thing that we depend upon is the low entropy form of the hot spot in the sky being the sun, and the low entropy dark comparison between the hot spot and the dark sky. Now, what is it about the sun? Well, you have nuclear physics and all that sort of thing going on. The main thing to know about the sun is it's there at all. And it's there at all because of gravitation. And we don't have this uniform distribution because of it's been clumped into stars like the sun. This is what we live on. Can we move to the next slide, please? You see, the remarkable thing, the remarkable thing about the singularity is that the Weyl curve in the Big Bang is 0, very, very small, with the Weyl curvature of a black hole goes to infinity. So to me, this is a huge problem. People would argue, oh, well, to understand the singularities, we need to do quantum gravity. And I believe the same thing. We need quantum gravity. That's how we want to end. But it's a very, very strange quantum gravity because it has to behave completely oppositely with regard to the Big Bang curvature.